Thanks, Chip. Okay, I think we have the microphone working. Can everyone hear me in the back too? Okay. So this lab was labeled data entry and management organization. I'm going to do 2 little mini lessons because we don't really have a lab right now listed going over like basics in R and R Studio. So I'm going to do a short presentation first on the R environment, what the program looks like, and the basics that will help you understand if you're brand new to R or if you're kind of maybe a little bit familiar. Hopefully this will give you some reference guides. And then we'll move into actual coding and do an example of how to get from your just data set to a network object before the later presentations go into some more metrics and visualizations and actual analysis. And feel free to stop me if I say anything that doesn't make sense, or if you have any questions, or put it in the Slack and Gabe or Madeline or any of the other IAs will shout it out to me. Okay, so first, I'm just going to go over a little bit on what R is, the difference between R and R Studio. Usually we're going to talk about R all the time, but what we actually mean is R Studio. What packages are, so if you did the install sheet that Gabe and Madeline sent out last week, you've installed a bunch of packages, and it's helpful a little bit to actually understand what those packages are that you've installed. And then just some basic getting started in R, more data workflow type stuff that I think is useful to know beforehand. I didn't learn it till like after, and I wish I had learned it in the beginning. So that's what this kind of reference slides are for. Some general tips as you're going through R and these workshops, and some online resources for further use, cheat sheets, and different packages you can use as you're going through all this stuff and getting to know R in general. Okay. So what is R? If you have done any sort of quantitative programming before, you know generally a statistical program software like Stata or SAS, SPSS. R is unique in that it's an open source software. So all the packages and functions we use, most of them are created by people who just wanted to do it. So it's not as regulated as more official programs that you might be used to, which is awesome because it's free and it's entirely user created, which also sucks because stuff doesn't get updated as often, and so something that you might have used last year might not exist anymore, or things might not have been updated. So there's ways to troubleshoot to kind of figure out and make sure that you're using the right versions of everything, and that the packages you want still work, and how to figure out what you need. So R itself is its own coding language and an environment. Really emphasize the language part because it has its own grammar and syntax, and when you're new to it, it feels like learning a new language in that, 1, it takes a lot of practice, and 2, it's really frustrating. It's an object-oriented language, which that's a weird term in general. What that means is any process you do that you want to save, you have to give it a name. So if you're used to Stata or SAS, you might just be used to doing kind of functions that do something to a data set and that it automatically saves in your environment. In R, stuff's only saved if you give it a name. And I'll go through a little bit. We'll do some examples to see what that means when I say object-oriented environment. It just kind of sounds funny in the beginning. And like a language, it's a pretty steep learning curve. It's really frustrating in the beginning. When I've taught undergrads, I said if you feel like you want to throw your computer out a window, then it's fine. That's how everybody feels when they're learning it. But as you keep going, I promise it does get easier. You just got to kind of get that tipping point in there. And all the RAs here are here to help. And the hordes of computer science nerds on the internet who are willing to help if you're nice to them. Who might not always be nice to you, but they're helpful at least. So we use 2 programs, R and R Studio. R is the actual statistical programming language. So when you've downloaded it, you downloaded 2 things. You downloaded R and R Studio. You can think of the 2 things, R as the engine of a car. It's the actual program that does all the work, that gets everything up and running. To most of us, if we just have R, it's completely useless to us. If I have a car engine, I can't do anything with it. R Studio is the IDE, or Integrated Developed Environment, which is a program that incorporates R and allows us to save files, to see what everything that's going on there. It's basically our user interface. So with the car metaphor, R Studio is basically your dashboard. That's how most of us interact with an engine, is through the dashboard in our car. So when we talk about R, we're usually talking about R Studio because that's how all of us interact with it. Unless you're like a super stats person, I've seen them using just R, not R Studio, and that's way beyond anything I could do. So when you open R Studio, for the first time, you'll see this window that's separated into 4 elements. As you see some of us going through our own R studios, you'll see the colors are different. You can change the colors if you want based on what's visually preferable to you. So it won't always look like this, but it's the same basic layout. And I'm going to go through each window and what it's for. So every time you open R to do anything, you're going to be opening R Studio. So these 4 panes are your source, your console, your environment/history, and this last one, which has a bunch of step windows on it, it's your files, your plots when you plot anything, where all your packages you've had installed are, and then a window for help where you can look up documentation for any packages and find out what the different functions are and how to use them. So the source is where you're going to be writing all your code. Anytime you see us opening anything and editing code, it's going to be in your source pane. I clearly didn't edit this when I taught it to undergrads last time because I have the homework assignments in there. But everything that we do here will be in an R Markdown or R script format. R script is basically just like a text editor where everything in it is run as code unless you tell R not to run it as code. R Markdown is a type of file that incorporates plain text and code that can be rendered into a PDF or HTML. So this presentation I made entirely with an R Markdown to be able to output and show to everybody. So that's where you write all your code, and you should write everything down and comment it so that you can go back to it later and see what you did or continue on the work you're doing. The console is your engine. So it's the engine part of R. If you were just to open the R program, this is what you would see, just this type of window. All the other windows are to help you interact with it. So anytime you run something in your source code or click enter to have the code run, you're going to see some stuff happening in the bottom there, and that's just the engine doing its work and running all of the functions that you told it to do. Sometimes you'll get output in the console, like if you do some basic arithmetic or run some models, things like that. But nothing that is in this window is saved. It just outputs what you told it to do. The source and your writing there is where you figure out how to save stuff. So your environment and your history is where your objects that you save go. So you'll see when we just start doing some stuff in R, anything you give a name will show up in the environment and history, and it also keeps a record of everything you've run so far in that session. Once you close out R, usually it'll clear that, so you won't have a record of the history, which is why you should always comment your code and tell yourself what you did, because you won't remember a few months later or even an hour later if you're me. And then finally, again, the files, plots, packages, help. Shows what's in your current working directory, and I'll explain what that is in a second. Displays what plots you have, what packages you have in there, and any instructions you might need help with. So just to give a little more detail, zooming in, this is an example of the source pane, so I've just zoomed in on the top left corner one, and this is an R script file. So everything you see with the pound or hashtag is commented out. So if you run that R, we'll just ignore it. So that's how you kind of write notes to yourself or give descriptions on what you're doing. Anything else, like you see the library, the different functions, those are code, and if you click on it, press enter, it'll run into the engine. But this is how you save your files and know what you've done in the past. Again, this is the console, so the engine, it'll tell you what version of R you're running when you first open it. Any warnings and errors will show up here as well. Warnings and errors are both in red, which gets scary sometimes. Red does not necessarily mean something's wrong, so just look specifically for what the wording is. You can also just do basic arithmetic. You can type directly into the console, but anything you type in there will just disappear once you close it out. Okay, again, so the environment, this is an example. I've saved an object. One of the training data sets in R is a cars data set. So you can see it separates them into data and values. So I saved the empty cars as an object, and I wanted to know what the correlation between horsepower and weight was, and I wanted to keep that number stored. So I just gave it a name, horsepower, weight, and it saved that number that I can reference back later instead of having to redo the correlation function over and over again. And here's kind of just an example of if you want to view your data like a spreadsheet style, what you can do is just click on the empty cars object in your environment, and it'll pop up in your source window and just look like a spreadsheet. And that's something I and many of us would highly recommend you doing the first time you open some data, which we'll do in a second, is just look at the data like in a spreadsheet format, because you can pretty quickly see any weird or wonky values or weird structures that you wouldn't if you didn't just physically look at the data. Okay, and your files in the bottom right-hand corner, this is where you're going through your working directory. So working directory means that R, whenever you open R in a file or working with it, it's always pulling stuff from a specific folder, and you can tell what folder it is you want it to pull stuff from. And so what I would recommend during this workshop is you have one folder for the whole workshop and keep all the files that you see on the drive in there. As we're pulling in data and different R scripts and stuff like that, it's much easier to have them all in one place, and then R knows where to pull them from. Because if you tell R to pull a specific data set, it's going to go to the working directory it's currently in, so it expects that that data set is in that folder you're working from. This bottom right pane is also where any plots you make will show up. So if you make a bar plot, network graph, whatever, it'll show up in this bottom right-hand side so you can see it, and you can export it or zoom in to save it to use for publications or presentations later. So the list of packages you've already installed that on the script that was sent out earlier last week, all of those packages are going to be in this little window here. It'll show you also some other ones that are preloaded in R. If you look and see, there's a checkbox next to one of them that's called Broom. That means that Broom is currently loaded. So we'll show you how to load packages typing in code, but if you want to, you can just go to the package pane and click the little checkbox, and that'll load it for you. You can also uncheck it, and it'll detach the package, which is useful if you're going between iGraph and StatNet, which are two network packages that do not like each other. You really shouldn't have them loaded at the same time, so if you're going between them, it's good to just uncheck one of them and keep the other one checked in. They have some functions that are the same name, which is super fun for us. But so unloading one of them will make sure that R doesn't get confused when you're trying to run stuff. And then any package that we've told you to upload, I think maybe including IdeaNet, will have its own documentation. Yeah, okay. Have its own documentation that if the package is in your RStudio, then it has the documentation in there as well. So if you're looking for how to fill in a specific function, what the arguments are, what it can take, or some examples, you can go to the help pane, type in either the package or this function you're looking for, and you'll be able to find the documentation. Some packages are better documented than others. iGraph is very well documented, in my opinion. I believe IdeaNet is also very well documented because I know the people who wrote it. But some are very unhelpful. And the ones that are unhelpful, usually people have gone online and figured out what to do. So there's always a way to get help to figure out how to use a package if the documentation itself is not great. Again, it's all open source, so people are writing this, and it's not as peer-reviewed as other packages. There's also a viewer pane, and what that one does is show if you do any kind of HTML rendering or tables that uses HTML code, it'll output in there. So the file, the markdown file I'm going to show you next that we're going to work through, you can render that and it'll output the whole code and everything we've done in the viewer pane. And if you're doing any kind of creating PDF file or creating HTML files for blogs or descriptions of what you've done, it's a good way to kind of check how things are going to look once you're done with the code. Okay, so I've been talking about packages a lot. There's a specific process for getting packages onto your R, so you've all already installed the packages. When you install a package, you only have to do that once unless the package updates, which it will. You use just install.packages and then the package name in quotes. And then when you want to use the package, you use library and the package name, no quotes. Don't know why it's different, just to be confusing, probably. You can think of installing packages as putting in the light bulb and then the light switch as the library function. So you've already installed it, and then in order to use it, you have to hit the switch button, which is our library function. Okay, this is just a list of not exhaustive packages that we're going to be using throughout this week. Ones that are used pretty frequently. So we have Tidyverse, which is a collection of packages written by the team that works with RStudio, which is now called Composite. And it's functions to manipulate and clean data. It has a lot of syntax that's similar to SQL, if people are familiar with that. I find it much more user-friendly than using base R functions and cleaner. And it's easier, the data flow's a lot easier using these functions. So any functions that you see me using cleaning data probably come from the Tidyverse. IdeaNet for processing, analyzing, and visualizing networks, which Tom will go into more detail later. Tom and Gabe and Others on the DNAC team have been working on this for a long time. That's supposed to be a easier, more user-friendly way of doing a lot of the stuff we're talking about in terms of network metrics and creation that can help get you started. iGraph is another package for creating, manipulating, visualizing, and analyzing data. I'll be using that, showing you how to get a network object started in R. gggraph for visualizing networks. You can visualize networks with iGraph. I prefer gggraph, and I think Gay will be using gggraph to show some visualizations later this week. We prefer it because it's similar syntax to ggplot2, if any of you are familiar with that, so I find it just more user-friendly and prettier than iGraph, which is the most important part. And then finally, StatNet is the statistical methods for analyzing networks, so when Jim goes over doing like exponential random graph models later, we'll be using that. Again, StatNet and iGraph don't like each other, so I'm going to show you in a bit how to, if you create a network in iGraph, how to translate it to something that's usable in StatNet that can go back and forth to each other. I think creating graphs is much more fluid in iGraph, so I'm going to show you that way, but I'll be sure to show you how to get it to a StatNet object as well. So I mentioned create some tips with getting started. Make sure you create a folder for each project you do, or in this case, this workshop, on your computer, on your cloud-based folders, whatever you use, and always set your working directory, so whichever folder that you want it to pull from to that. So you can do it in code. I find that kind of finicky. I prefer to do it just by point and click. So when you're in your RStudio, if you click Session, set working directory, choose directory, you can just manually pick the folder you want to work from. Okay, and so some quick symbols that you're going to see around here just to know what they mean. The C and parentheses is a function that takes comma-separated numbers or strings and joins them together in a vector. So you'll have, if you use the C function, you're creating kind of just an object that has a list of numbers or strings attached to it. The arrow dash, which is just literally a less than and dash sign, is the assignment operator. So when we talk about it being an object-oriented language, you give a name, the assignment operator, and then what you want it to be. So for example, if I want to create this vector just of these 4 numbers, I can give it a name called myNumbers and assign it the list of numbers 1, 2, 3, 4 to that vector. So now myNumbers, that object, means the vector that contains 1, 2, 3, and 4. Objects are case sensitive and can't have any spaces in there. So if you use capitals, whatever, you have to do that exactly. All of R is case sensitive, including functions. The percent greater than percent is called a pipe operator. Directly translated to English, it means and then. So if you, instead of doing a bunch of functions around each other, you can pipe what you do to the next thing. So if I wanted to take myNumbers object and get the mean of those 4 numbers, I can do myNumbers pipe to mean, which directly means take myNumbers and then calculate the mean. And it's the same thing as just running the function mean on myNumbers. For something as simple as that, it's not entirely necessary. When you're doing a lot of steps in data cleaning, the pipe becomes really useful rather than doing a bunch of separate lines of code. I've seen this a lot more recently, though I think the percent version of pipe is still the most popular. You may also see on Stack Overflow or other people writing the pipe as the kind of bar and then greater than instead of the percent one. Okay, some general tips as we're going through. Do not run all the code at once. Even if it works, you're not going to know what each line does. I would recommend running code 1 line at a time, and I'll show you how to do that if you're not familiar with R. If it doesn't run, if something throws an error, you're not going to know which line threw the error, and it's going to be really hard to debug the code rather than just going 1 step at a time. I feel like that's more of a tip I have to tell undergrads rather than this audience, because they just want to run through everything all at once. And then it's going to sound kind of funny, but just for errors, literally just copying and pasting the error into Google is how I solve most of my problems, and you'll end up landing on some kind of Stack Overflow page, which is where all the nerds are that can help with what you're doing. You can also create a free account. The best thing I was ever taught in grad school by one of my friends was how to write a Stack Overflow question so the nerds don't get mad at you and they actually do help you. If anyone wants tips on that, I'm happy to share, because I've had pretty good success so far. No one's yelled at me on the internet. And just in general, as we're going through all these workshops, there's a lot of different ways to do everything we're showing you. the ways that we're showing you, the way that I'm showing you how to create a graphed object or use R is just basically how we were taught. So there's different ways you can find online, and it depends on what we were taught first. So for me, it was lots of being in this workshop 5 years ago. That or whichever Stack Overflow page you happen to land on first is usually how people do it. So if you find a better way than what I'm showing you, this is not the only way to do it. It's just the way that I think is the most intuitive, and it could not be the most intuitive for you. So I won't be mad if you don't use this way. It's just a starting off point if you're unfamiliar with these methods. Okay, last thing before I switch. There's a couple of resources that I've liked that I use that are helpful. So a general R guide, I think a grad student made this. It's a book down, so a blog that she made in R as well. And just a general guide to R that helps you with some like tips and tricks, more so in more detail than I've done here. R cheat sheets, I think it's gonna be posit.com now, but that link should still take you there for basic packages that we use like in the tidyverse and like some very common methods that you'll need to manipulate data. There are some really good visual cheat sheets that can help you figure out how to do that. And then there is a professor in the sociology department here at Duke, Kieran Healy, who has a book on visualization in R specifically, and I found that book extremely useful when trying to do visuals. He does a little bit of network stuff, but it's mostly just normal data stuff, and he has the whole book free online. I found it very helpful, especially if you're trying to make stuff look pretty with colors, and I think that's fun, but maybe that's just me. Okay, so I'm gonna move now to the R lab. Are there any questions so far? Okay, cool. One sec. Okay. Does it need to be bigger in the back, or is that okay? Good, okay, cool. Okay, so now we're gonna actually move to the data entry and organization management. Hopefully the little intro to R is not totally review for everyone. What we're gonna do in this lab is how to go from just a data set you have with network data in there somehow to the actual files that you need to create a network that Jim talked about in the last presentation. So this is an R Markdown file or .rmd. You might also see it with the new RStudio. Some people use QMDs. Basically, again, it allows us to combine regular text, plain text, and code. So you can render it into like the presentation I just showed you. I made it in R. Some people write all their papers in R because it really makes it really easy to add visualizations and tables in there as well. I like it when I'm teaching because it forces students to run things like smaller chunks at a time. They can't just run the whole thing. We'll go through this and just credit where credit's due. This entire tutorial I did not come up with myself. This was adapted from Maria Cristina Ramos's data cleaning for SNA tutorial from 2019, which is how I learned most of the stuff. Maria Cristina is another DNAC and Duke Social alum, and she's now at Florida State University, I think, as an assistant professor. Anyway, she's awesome. I've made some changes because, of course, this was made in 2019, so now lots of the stuff doesn't work anymore. Or some of the stuff is a little outdated. Some of the errors she was troubleshooting are no longer errors, which is nice, that have been updated since. Okay, so with an R Markdown, you're gonna have text like this, which is just plain text, and then these little, what we call chunks of code. So anything that starts with the little dashes and then the parentheses or the brackets with R is a chunk of code and can be run just like you're running an R script. So if you wanna run anything in here, you can run the whole chunk if you want to, or you can run it one line at a time. So if you wanna run it one line at a time, you can highlight it. And then if you're on a Mac, hitting Command Enter will run it. If you're on a PC, it's Control Enter. So if you look here, I just created an object. No, don't want to do that. Actually, sorry, Gabe. It's not my computer. So here, I highlighted this little code. I wanted to create a vector like I did before with 1, 2, 3, 4. And now in my environment, you see I have this little object called A, and it tells me it's a numeric vector with range 1 to 4. So it automatically detects that it's numbers and not strings. So I can take the mean of A, give me output here. When you're in an R Markdown file, instead of all the code results outputting in the console, it'll just output right underneath the chunk, which is neat. I can also create an object if I want to that holds the value of the mean of that vector. So I gave mean A as an object of the name, and it just holds the value 2.5. So if I just run the object, it's the same thing. So if you want to hold more complicated calculations or values in its own object format, you can do that here as well. And that's again what we mean by object-oriented language. If you want to just run the whole chunk, if you know it's going to work or if it's just doing one thing, you can also click this little play button here, and it'll run everything in the chunk. You'll see it highlighted green there for a second. That means everything ran smoothly. If you run into an error, you'll see a little red light pop up, and that means something went wrong, and you'll see the error notice will pop up as well. Okay. So the contents of this tutorial, what we're going to do is first go again over, Jim mentioned this in the last presentation, but the files you're going to need to create from your original data set for social network analysis. You'll see SNA a lot as a shorthand for social network analysis. And then we're going to go through the process of how to get from your raw data to constructing a network object and checking to make sure everything looks okay. So the first thing you're going to do is inspect or evaluate your raw data. So physically looking at the spreadsheet format and looking at like what columns you have. We're going to pretend we have a code book for this, referencing back to your code book so you know what the values mean and how you might have to edit it. And then the third step, which is also something I learned from Maria Christina, is making a plan. So in this step, we literally don't do any code. You like physically write down what your plan is, which I find when I actually remember to do that, I run into a lot fewer errors. And it's also useful if you're writing up reports or papers later to know exactly what you did if people have questions about your code or as you're describing how you used the data. Then so we have our plan. We're going to manipulate the data as needed and construct our network object, and then check to make sure that it looks like we're going like we expected it to. Make sense so far? Okay. Okay, so the two files we need that Jim mentioned earlier is a node list. So a node list is what you kind of were used to seeing as a data frame. It's basically just detailing the individual nodes you want to include in your network. So every row in the data set is just a person, or if you're working with organizations or whatever your unit of analysis is, that's what the row is. And then all the variables are the attributes that you might want to keep to visualize in your network or use to analyze if you are interested in how people are similar or dissimilar and such. I'll also note that I've written a lot more here than I'll say, just to have you have something to reference back to. So I'm not going to talk through everything that I noted out, just so you have those notes later. So just as a short example before we go into some more real fake data, we would create a little object called myNodes. This function creates a data frame, and then I've just included 3 vectors. So when you combine vectors together in one object, you create a data frame. So I'm going to highlight. You can also just put your cursor at the beginning of whatever the argument is and press enter. So it looks like it worked, it went green. And so now if I just look at my nodes, you'll see I have a little data frame where I gave each person an ID, what their gender is, what institution they belong to, and their name. And those are just details on the individual person that I want in my network object. I can also, if I want to look at the data set, click on it here in the environment. It'll open up as a little spreadsheet here again. The second file you'll need is the relationship structure. Again, this is like your edge list or adjacency matrix. I'm only going to show you what an adjacency matrix could look like in an edge list. I find those are the ones that I see the most. I primarily work with edge lists. I find them a little easier, especially when you're working with people and have to have different weights or characteristics of those ties together. So in this little chunk of code, I'm going to create an adjacency matrix that's completely random. So just creating a blank matrix and then filling in some names. So I'm adding some random numbers here. And then as Jim mentioned in the previous one, a matrix has the same exact people or numbers on the columns and the rows. So I'm going to name the columns the same names as our previous network, and I'm going to give the row names the exact same column names. And then one thing you want to note in the matrix is if it's kind of means something in the diagonal, if it has a value or not. So most of the time, if we're looking at, like, let's say I work with friendship networks a lot, it doesn't make sense to have somebody nominate themselves as a friend. So everything in the diagonal where the person would cross over themselves should be 0. Some people will nominate themselves, but if it's not useful to us, we'll make it 0. So most of the time you'll see a 0 in the diagonal, or you'll have to edit it to that, unless having what we call a self loop, so a self-nomination, is like meaningful to you in your data, which it could be depending on the type of data you use. But I'm just going to make it a 0, because in this network we don't do self-nominations. And then we can just look at this adjacency matrix, so you can see all of us are in the rows and the columns. And if we're tied together, there's a 1. If we're not tied together, it's a 0. And the whole diagonal is a 0 because we don't have self-loops in here. Matrices are obviously way more easier to see when they're very small. Once you get to like more than like 50 observations, it's much harder to kind of see what's going on in the matrix or like identify the ties with each other. Matrices are also useful when you have valued relationships. So I work with bullying data. And here you would see 0 to 1 because the tie is present or not. In bullying data, if I bully Gabe, there would be a -1 between me and Gabe. And that gives you a sense of like what type of relationship that is. Or if this is a data set where it's how often we talk to each other, you might see values greater than 1. So if I texted Tom 3 times this week, then there might be a 3 in there. It depends on how you're collecting the data, what question you're asking, but it can show up in a variety of different ways. So we're going to end up using an edge list here, which I find a bit more intuitive and ends up being useful. So I'm just creating a random edge list. So the edge list will always have at least 2 columns, the from column, so who is doing the nominating, and the to column, so who's being nominated. And then I'm adding an edge weight just to see what it looks like. So here we can see the data set popped up. We gave ID numbers to the previous node list before, so we can connect that back to those people. So 1 nominates 4, and the weight, whatever that means, whether it's times of contact or strength of tie or something, is added in the end. So once we have at least one of those relationship structure files and a node list, we can combine those two using iGraph to create our graph object. So in iGraph, the network is a graph object, and StatNet, it's a network object, which are essentially the same thing, just given different names because they're different packages, but a graph and network are interchangeable. So here we're turning on the light bulb. I'm going to load library. And then the function in iGraph, if you have an edge list and a node list, is graph from data frame. The D argument is your edge list. Vertices, another word for your actors or your nodes, is your node list. And then because this is ostensibly a friendship network, I care about who nominates who, so I'm going to say directed equals true. If you don't care about who nominates who, or if it's a sex network, like Jim mentioned before, that's all the relationships are binary, then you would have directed equals false, so that a tie is just a tie. It doesn't matter who nominated whom. So run that one. And then the first thing I do, as soon as I have a graph object, is I plot it. Networks are very visual objects, and so usually you can figure out if something's really wrong just by looking at the plot itself. And you'll see a little network of all of us, and the arrows represent directionality. So here we Gabe nominated Tom, Tom didn't nominate Gabe, and those directions can be meaningful depending on your network data. Okay, so that's a little toy example. Now we're going to do a slightly more real toy example with some synthetic ad health data. So it represents an example of what data might be in ad health that Jim mentioned before, but it's all fake data, so that no privacy issues. First, we're going to go over the process a little bit, and then we're going to go through what the process is. So the process that you go through when you're going from raw data to a network object is, again, first inspect and evaluate your data, identify what you need from the data set to get to a network object. So what's going to be your ego, your node IDs, and the different attributes you need. So you need information on sex, gender, if it's a bipartite network, if the groups they belong to, things like that. What pieces will be the edges. So in ad health, it's a friendship nomination. So it's the columns where it has the IDs of the friends that the individuals nominate. We need those for our edge list. And then once you know what you need for your network object, you're going to need to identify any issues you have with your data that you'll need to deal with in the cleaning stage before you can even make your network objects. So if there are any issues at the observational level, so if you have extreme values, nonsensical values, or values for missing data that haven't been converted into missing data yet, so 9s for missing, or if something doesn't make sense. Like I think there's one person in Ad Health that reported having sex like 100 times or something in like a week, which they were 15, so it doesn't make sense. So whether or not you cap those data or not, or just remove the observation, those are decisions you make obviously as a researcher who knows your data very well, but you want to make sure that you do that before you get to the network object, because then you're going to have to go back anyway. If you are using something like Qualtrics has its own messiness to it when you're downloading the data that has to be cleaned before you can even get it into like a useful format. So just making sure the data is as clean as possible and finding out what you need to fix before going to the network side. Again, try your best. I know like I do this all the time myself. I start jumping into code before making a plan, and then I ended up having to redo everything anyway. So try your best to actually make a plan first. I know the code part's the exciting part, but it ends up being way better if you do it. So we talked about looking at the data, and so I physically will write out what I need to change just so I have a record of it as well, because stuff can get lost, and then it's really confusing when you're trying to write everything up. So plan the changes you're going to make at the observation level, what you're going to do with missing data, any recodes you have to do, and then plan the tasks you're going to need to restructure the data set. Do you want it in an adjacency matrix format? Do you want it in an edge list? And just write all these out. And then we're going to construct our network object. So hopefully everything's clean enough that it works to make our little graph. Usually the actual process is going back and forth between these steps multiple times as things don't work or things don't look right. But hopefully making the plan and doing it that way will end up being better for you. And then obviously check your work. You want to make sure everything makes sense and is working the way you expect it to do. Okay. So I am going to load tidyverse, which is again the package I use to clean data. And then hopefully this is, oh, I didn't even do this. You should have done this in the beginning. Yeah. Make sure that we're working from the right directory. Sorry, Gabe. Okay. So I saved this synthetic Ad Health data in that directory, and so because I made sure that the folder I'm working for has that file in it, this should work. Yes, okay. So it's a CSV file, so read.csv, and so I don't have to keep loading the data. I give the CSV file a name, which I've just labeled it for the Ad Health, and you can see it in my environment here. We've got a ton of observations and almost 40 variables, and so if I want to just look at the spreadsheet, I can just open it here and see that. And so we're inspecting our raw data to structure to make sure we understand it. And so usually opening the spreadsheet is the first thing I do. And already right away I can see some issues with it in terms of we're going to have some missing data. We're going to have to recode some missing values. Those 999s are supposed to be missing values. So keep that in my head as I'm working through this. We can do some basic functions to see the structure of the data. So the class function will tell us what type of object it is. So it's a data frame, which is what we want it to be. Other types of objects that exist in R that are not as useful, but data frame is where you want it to be right now. And it's kind of hard to see if you just look at this what all the columns are, especially if you have more than 50 columns or measures. So if we run the call names part, it'll just give us a list of all the column names in there, and hopefully you have some sort of code book that'll tell you what all these columns names refer to from the measures in your data set. Another good function to use is the glimpse function, which will tell you every column name, what type of vector it is. So if it's an integer, if it's a string variable, if it's a factor, some factors are specific to R itself, but integer and double is another R one. These are all numeric vectors, and it'll tell you kind of the first 15 or so observations for each of these. Okay, so we looked at our codebook and our survey, and we can see that the ego NID is our respondent's ID number. All of the MF NIDs are the male nominees. So in Ad Health, they were told to nominate their 5 male friends and their 5 female friends. So the FNID are the female friends. Sex refers to the respondent's biological sex. Grade is their grade. And the ComSent value is whatever school they're in, because Ad Health had a bunch of schools, different schools, obviously. Typically, we usually plot one school at a time, just because it's already messy enough. You can put different schools together, but for the purpose of visualization, we're going to look at one school. And so again, the initial red flag I saw was that the 999 values in the nominations should be NAs, so we'll change that soon. We can also just get a quick summary of the distribution of all the variables. So if you do summary and then your whole data set, it'll give you a 5-number summary for every variable in your data set, which may or may not make sense depending on what type of variables you have. If you have strings or categorical variables, you'll get weird stuff there, but for all these numeric variables, we can get the general distribution of these numbers. Again, might not want to do it for the whole data set if you have a lot of variables, but it's a useful, quick visual look at everything. So I also want to see a couple of things just to get an idea of the data set as well. So obviously they're schools, so they are by grade. So I want to see how many students are in every grade. So it'll list all the grade values, and then how many students in all of them, and maybe how many people are in each racial category. A red flag for me here is that there's a 0 for racial category, so we need to make sure, go back to our code book, figure out if 0 means an actual category or if those should be missing for race. Again, you just want to jump through all of these little checks just to see what's in the data so you can make your plan. You can also run a couple of crosstabs. So I wanted to see what the sex distribution is by grade, so I just do with the data set, table, sex, grade, and then we're just ignoring the NAs for right now. And then just a simple looking at the sex by the schools, just to see if there's any kind of outliers, like this one is weird. School 27 seems to only have girls. So things like that you'll want to go refer back to any data documentation later to make sure that your data doesn't look funny. And then we can also do a couple of visualizations. We could do a bar plot of the total nominations people have, so see how many friends, the distribution of number of friends. So quite a lot of people didn't nominate anybody. Otherwise, we see a little bit of a curve for who have nominated a number of friends, 1 through 10. Okay, so now we're going to make our plan. So again, no code involved here. We're just going to think about what we need to do. So plan for our unusual observations. My plan here is to convert all the 999s to missing and remove them. Because for our edge list, we just care about who's connected to whom. Figure out on the documentations if our 0s in race are a real category, or if they're in A. I checked the documentation. They're actually a real category, so we'll keep them. And then our plan for constructing a network, so pick what type of network structure you want. In this case, I'm going to create an edge list, and then describe a series of tasks you're going to need to do it. So just as a reminder, how an edge list looks. We don't necessarily need the weight in this case, but we do need at least 2 columns, one that is from, so who the nominator is and who they nominated. And so this is a long form data, which means that instead of the adjacency list that Jim showed before, where it's one person and all the people they nominated, each row is a different pair. So you'll see multiple people pop up twice and have multiple rows for each other. So my steps for constructing the edge list, I'm just going to pick one school to plot and look at for now. So I'm going to look at school 7. I'm going to convert the nominations from wide to long format to get that edge list. I'm going to select, make sure I have the right ego and alter. Alter, if we haven't gone over, is who ego nominates, ego and alter IDs. I'm going to remove the missing friend values and the crazy 999 values. So for this particular tutorial, we're only going to look at people who have a connection. So sometimes isolates are useful to have in knowing who's by themselves in a network. Sometimes you just want the people who have ties together. So we're going to actually start by constructing our edge list and then create our node list from that, so we make sure we match all of the edges and nodes together. So here I'm doing my first edge list creation, which is just filtering out all the schools except school 7. And we can use head to test that it worked. So that gives you the first 6 observation in a data set. So here you can see all of the values for school or 7. Something that I do as well is every time I create an object that I'm editing, I give it another number so that I have a new object every time, and I'm not constantly rewriting over my object, because I could just name this again AHS edge list, and it would rewrite the one we just made. And for a simple code, that might be fine, but it gets really annoying if you have to then redo everything if you make a mistake later. So here what I'm doing is I'm taking this previous edge list, or the previous file we made, and I am selecting that object, the ego NID, all the male friends, all the female friends. The colon tells R that you want all of the columns between these two columns, so if you know the order of the columns, that's useful. And then my pipe, I'm going to use the tidyverse function to pivot longer. So to take it from a wide data set to a stacked long data set, I'm going to tell it to make all of the columns that are not ego's ID stacked. So we get one row per two people. And I'm going to run head again just to see it. And it looks like it works. So what it did is it took the column names and it made it its own kind of value. We'll get rid of that later, so we're just left with the two columns, but we have our ego NID and our value column. And the value column ends up being those ID numbers of the students that they nominated as their friends. And it might be useful to keep, in this case we're not. The name says what the column name was before for that value, so if you want to know if that's your male or female friend, you can keep that. In this case, I'm going to get rid of it because we already have their sex described in their node attributes file. So I'm going to create another file, edgelist3, and I'm going to only select ego NID and value, and then I'm going to change the name of value to alter NID. So I know for my own reference, these are the egos and these are the alters. So now we have a little data set, or this is a tibble, which is a similar type of file, with just egos and alters. But as we can see, we still need to fix the 999s, and then it automatically moves even the missing values in there. So we'll get rid of those because we don't need those values. Okay, so what I'm doing here is I'm taking the previous file, I'm doing NA omit, which just deletes the rows that has an NA value in the alter ID NID column. And then I'm filtering out, so anyone that has an alter NID of 999, I'm also removing those because we know those are NAs and we don't need them in our edge list. And then I'm just going to check again. With the head function, the automatic version is it shows you 6 rows. I'm telling it to show me 15. Here we have a cleaner version, so now our edge list is just the ego's ID and everyone they nominated in stacked format. So you'll see ego 1 has 6 or 7, I can't count, different rows because they nominated that many friends. Are you with me so far? Do you have a question?
You said the 1, 2, 3 are the IDs of the...
Yeah. So ego 1 nominated this person whose ID in the data set is 1, 2, 3.
Oh, so it's not 1, 2, and 3.
Correct, yeah, so this is an edge list, so it's just 1-on-1. These are just their ID numbers. Okay, so we have our edge list, and now we're going to use our edge list to create our node list. So for our node list, we need everybody. So everyone that's in the ego and the alter column. Sometimes you'll have people who were nominated but did not themselves nominate anybody else. So we need to stack those two columns and just get out all the duplicates so we have every single person in the data set. So what I'm doing here is I'm creating a vector where I take our edge list file, with the last one I used was edge list 4. The $sign calls a specific column in that data set. So I get the ego values, comma, the alter numbers, and I use the C function at the beginning to create a vector. So now we can see in our environment here, we have AHS nodes, which is just a vector of all of the values as many times as they showed up. And you can see in here as well. The first ones are just all ones. So what I'm going to do is I'm going to take that nodes file and make it a data frame. Do you have a question? No. Make it a data frame. So now it'll show me the first few rows. When you have a data frame like this, R assigns its own kind of row numbers. So that's what this is here. It's not actually part of the variables you have, but these are all of our ID numbers. here what I'm doing is, because we have duplicates of every ID, because we had that long data set before, which had every possible combination, I'm going to use distinct, which means only keep one of each observation. And then I'm going to rename this, because it kept the column name as AHS nodes, to ego NID, so it matches our edge list. Because you want to make sure that the column name for your egos matches your edge list and your node list. We're going to check to see how it worked. And it looks like it did, so it looks like in the order, we only have one of every observation. Okay, so here what I'm doing is I'm going back to our original AHS WPVAR CSV file that we loaded. That has all of our attributes in it. And I'm going to join it with this list of nodes that I have that are in the ego, in the edge list. So we actually had more people in the original file than we kept for the edge list. So this way I'm just pulling out the information of all the people that we need information for. And then doing the head. So now we have something that looks exactly like our original data set that we pulled, except it only has the egos, the observations that we took from our edge list. So it's a little bit of a smaller data set. I think it's like 440 observations, where the original data set had 447. So we just basically filtered out the isolates. Yeah?
Can I explain the left join?
Yeah, good question. Okay, so join is a function in dplyr in the tidyverse. And what it does is it takes our nodes file, nodes2, so this file we created here, and it merges it with our original CSV file. Left join means that I'm telling it that our primary file to join on is the left, so the first file that shows up. And so what it does is it finds every matching ID value in the AHS WPAVR, and it combines it with the nodes file. So we get all of the attributes from there that are connected to it. So you want to make sure that you have a matching ID column, so we have ego and ID in both of them, and it joins based on that key variable. Does that make sense? Okay, cool. Thank you for that. Okay, so we've joined this, and we run here. But initially, it looks like it worked, and then it looks like something's wrong. We should only have one value of 1, and we have a bunch of them. And as I remembered, as I did earlier, we actually initially filtered out on school 7. We kept only school 7. And so what I'm thinking here is that it's likely that every school has the same ID values. So I'm going to check that. I'm going to look at our nodes and see if there's a bunch of different ones for each school. Let's save it as an object so I can rerun it. And it doesn't look like that's the case. So again, our comsint value is our school, and I didn't filter out in this stage, so every school has its own one person. So we want to do is filter out so that's just school 7, because if you remember in the beginning, I said I just wanted to plot school 7. And in this case, all the schools seem to reuse ID numbers, which will get confusing. So I'm going back to the nodes file I created when I joined the attributes and the nodes, and I'm just going to filter so I only keep school 7 because that's the only people I have in my edge list. And I'm going to check that it worked. It looks like it did. You can do more checks if you want to, but just as a glance, it looks like I only have school 7 now, and so I have a unique ID for every person that won't screw up when I'm trying to create our network object. Now what I'm going to do, just for my own purposes, is just only keep the variables in the node list that I want to use for my network object. So I'm selecting the nodes file we just created, the ego ID I want, and then all else I want is the respondent sex, grade, and their racial category. I don't need any of the other variables for this network plot or analysis. And I want to make sure that works. Yep, so we see we get a data frame of 4 columns, and we see that we just have our ego ID, sex, grade, and race. Okay, almost done, I promise. Now we have our edge list and our node list. So you want to make sure when you're creating these that every person you have in your edge list also has a row in your node list. And that's why we made our list of nodes from our edge list so that we made sure they match, because R doesn't like it when you don't have an observation row in the node list. Even if you don't have any information on them, if all their values are in A, you want to make sure they have their own row in the node list. So I'm using this graph from data frame function again, and I'm taking our most recent edge list file and our most recent node list file and keeping directed equals true, saving it as AHS graph. So far it looks like it worked. I want to check what class it is because I know what it's supposed to be. So iGraph object, because we used the iGraph package. If you, like we had data frames before, if you use StatNet, you'll see it's a network object. And again, the first thing I do as soon as I create a graph to see if it looks funky or makes sense is plot it. So iGraph has its own plot functions and way to plot things. Again, Gabe will show you some other cool ways to plot things later. And we get this hairball. Usually the first plot looks really bad. Hairball is a technical term that we call for graphs that are confusing, stacked on top of each other and all squiggly. But on the cuff, it does look like what I expect. It looks like a school where there's clusters of some people. I'm going to make some changes to it just to try and make sure that it doesn't look super wonky. So what I'm doing here is I'm rerunning this plot. I'm going to color the vertex by the respondent sex so we can see if there's divisions by sex in the schools, like who's friends with who. I'm going to make the vertices smaller because they're a little too big now. They're stacking on top of each other. Because it's a directed one graph, we can get arrows, so who's pointing at who, who's nominating who. And I'm going to make the edge arrows size a little bit smaller. Yeah.
Can you scroll up a little bit?
Yeah.
Just the graph object. Can you explain to me what you're telling R on that first line?
This one?
Yes.
Yeah. So graph from data frame, I'm saying to iGraph specifically, take my edge list and create a graph. So the edge list is where it gets the connections, the relationship structure, and it makes this graph object with that. And I also want to add some attributes. So I want iGraph to know what each individual person's attributes is, so we add those attributes on it. Does that make sense?
Okay, yes.
Okay, cool. Sorry, thank you for your question. Yeah.
And when you say directed, then it's just going to assume that the first column calls the second column?
Yes.
Okay.
So if you had said undirected, then you would only need to have a dyad, these two people in there once. But when it's directed, you want to know who's nominating whom. So I'm interested in like friendship reciprocity. So I want it to be directed so I can see like, is this friendship reciprocated or not? Fun fact, most adolescent friendships are not. Yeah.
It's not direct as you just say equals.
Yeah, correct. Which you will in some StatNet functions. It only runs with undirected networks. But in this case, we'll use a directed one. Any more questions so far? Almost done as far. Yeah.
Maybe you can explain the other line as well, the where you plot it. So you just, when you say color, will it choose colors automatically?
Yeah, so it will choose colors automatically. There's a way to choose those colors yourself. There's in the iGraph documentation. This is just kind of to show that you can do it. But you can define beforehand what you want the colors to be. I'm just plotting it just to make sure it looks okay. I'll show you what the colors look like in a second. But basically what I'm saying is here, for the vertex color, V refers to the vertices. If I had put E, it would be the edges. So V, all the vertices of the graph object, take the sex of that person and give it a color based on sex. So if it identifies two categories, they'll get two different colors if this particular data set subscribes to gender binary. If you have more than one or you have some unknowns, you'll get more colors. Does that make sense? Okay. The edges, the connections, again, if it's directed, will have an arrow, and so I'm just making the size there. The numbers are kind of relative. You just really have to play around with it. I know from experience that that's the size I want. There's no like unit of measurement there. It's just whatever iGraph decides the unit of measurement is. And then just because it's a little too messy, I want to take away the names of the vertices. So I'm going to run this plot, and we'll get a little bit of a prettier picture. So it's still a little bit clustered because they're high schools and they're all kind of connected to each other in some way. This one's particularly looks like a denser high school with some little solo dyads on the side. But you can see it's a little easier to tell the nodes are not super on top of each other. You can play around. I'm not going to go too much into this because Gabe will go through it later when he does the visualization lesson with layouts and different algorithms that can arrange the nodes in a different way based on what you're trying to show. Or to make things a little bit clearer. But I usually do this just to make sure nothing looks crazy.
The split is junior high.
Thank you. Okay, last part. I'm running 2 minutes over, I'm sorry, Jim. Again, I mentioned before that iGraph and StatNet don't play well together, so we just created this all with iGraph. And so if you want to use the same object later, when Madeline does the StatNet metrics tutorial, we'll use this package intergraph, which takes our iGraph object and converts it to a network object. Nothing changes, it's just that now the object will work with routines that you do in StatNet. So we'll run this library command, and then I'm going to create a new object. I had made AHS graph before, but from intergraph, the function as network changes it to a network or StatNet object. So I'm going to run that. And then I can check again, if you remember up here when I checked AHS graph, it told me it was an iGraph object. Now if I check AHS network, it's a network object. And those are just specific to the different packages. And if I just want to make sure that it looks kind of similar, similar to what it was before, StatNet also has its own general plot function. So if I just plot it again, looks like it's the same one as before. They have both StatNet and iGraph have their own defaults for how they make networks, but essentially doing the same thing. Okay, so that's, I think, any other questions right now? If you come up with what stuff later, I'll be around. But that's essentially how you go from your data set to a network object, and then making sure you can go back and forth from iGraph to StatNet as you use different packages. Intergraph also has functions to go from a StatNet version to an iGraph version. Cool. I'll stop. Yeah.
So you said they don't play well with each other. So you're supposed to go to intergraph first, iGraph first, and then to intergraph?
So you can make a network object in StatNet. I think that iGraph is easier to make them. So yeah, so I created the network in iGraph, and then I used intergraph to translate it to a StatNet object. And then later, if you're going to be using StatNet to do any kind of calculations, you can use the StatNet object. Does that make sense? Other questions? Yeah.
When we start manipulating the StatNet, you said we do need to turn off the iGraph.
Yeah, I would recommend that just because they have similar functions. And you can do that again here, down below, where it says packages. The structure of your R might be a little bit different. You can move the panes around. So if I wanted to scroll down and find iGraph, I would just uncheck that, and you can see iGraph. Oh, because it's dependent. If there are dependencies, it won't work. So you'll have to unload a couple of them, but you can also, you'll be able to unload them from the start. Any other questions? Yeah.
I have a question. So in your step 3 main plan, so 3B was plans for constructing the network. Is that guided by theory, or is that more like a function of how you want this to perform, like in R?
I would say it's a little bit of both. I think with, at least when I'm working on stuff with networks, I'm usually incorporating like theory and R stuff. It's going to be primarily how you play with R, but if you want it, the way you want it to look in R is going to be based on the theory that you're using or what you think the network should look like. Does that make sense?
Yes.
Okay.
That's something we'll get to in some plans. Great.
Yeah, this is more the practical side. There's like other ways to think about it before.
That's helpful. Thanks.
Any other questions? Okay, cool. I will stop there and hand it back to Jim.
All right.